what I'm going to do is I'm going to skip section 3 of the chapter for just a second and go into the later section, then come back to section 3 because it would kind of tie in a little bit to what we're going to do in chapter 24. So I'm going to do a slightly different order than the book does. So I'm going to skip ahead to applications of Gauss's law in certain symmetries. So first one I'll do is cylindrical symmetry. So for example, suppose we have a wire, okay, and we have a charge on the wire, and the charge is spread out along the wire to make some lambda. Okay, now this looks pretty straightforward. And so let's say that I want to find, apply Gauss's law here. Now, I know by symmetry, if the wire is very long, then the whatever charge is here, some dq there is going to be exerting field this way, some dq there exerts a field that way. So the net field is always going to be pointing away from the wire. Okay, and so what I want to do is apply Gauss's law and see if that can help me figure out the electric field. Remember, we did a really nasty integral to figure out the electric field of this sort of symmetry before. And so we never want to do nasty integrals. We want to find ways to avoid them. And so we know that Gauss's law says that the electric flux, which is the integral around a surface of E dot dA, is going to be enclosed charge over epsilon naught. And so I want to actually apply that. And so what we're going to do is I'm going to say, okay, for this wire here that has some lambda on it, I know the electric field is going straight out, and I want a surface. Now, the electric field goes straight out in all directions, so I want a surface that's going to be symmetric with that. Well, the electric field is cylindrically symmetric, so I'm going to imagine a cylinder here. And I'm going to make it symmetric so the edge of the cylinder is some distance r away from the wire. Okay, and so we've now, my Gauss's law, integral E dot dA, okay, well there's three surfaces here. There's the left-hand end, the right-hand end, and then the sides of this. So we do the integral E dot dA on the left plus integral E dot dA on the right plus integral E dot dA on the side of the cylinder. All that is enclosed charge over epsilon naught. Okay. Now this looks like we're just making it tougher. Okay. But wait a minute. Dot product here. The dot product, remember the dot product, A dot B is equal to AB cosine of the angle between. Well, what's the angle between E and the surface on the ends of the cylinder? Well, the area vector is straight outwards, so that means it's perpendicular to E. Well, what happens when you do perpendicular? Its dot product is 0. So, bam, bam, those two integrals are done, okay, because they're 0. Okay, so I call that integration by obliteration. Okay, so we cleverly picked a shape. Now, if I had picked some other shape, that would not have been the case. But because I picked that shape, that made those integrals trivial. Okay. Now, what about the remaining one here? Well, we look at it and say, well, the E dot dA, well, the electric field's going straight out. dA is straight out, so that's just, so integral E dot dA is just integral E dA. Okay. Well, the electric field, because I cleverly made my cylinder symmetric around the wire, the electric field is constant, so that just becomes integral E integral dA. What's the integral dA? Well, that's just going to be equal to E times A. Okay, so A is the area of the side of the cylinder. Well, what's the area of the side of a cylinder? Well, that's going to be equal to the distance around here, 2 pi r times the length. Okay, so that's my integral. Now the next question is, well, what is the enclosed charge? Well, the enclosed charge is going to be lambda times the length of the thing. Okay, and so what we've got is, we've got E times 2 pi RL equals lambda L divided by epsilon naught. The L's cancel, so the electric field is lambda over 2 pi epsilon naught R. That's the same as 2K sub E lambda over R. Now, note that is what we got by doing a nasty integral before. So now we did this, what looks like a much more complicated thing because it's a surface integral, but it actually turns out to be a whole lot simpler. And so we've made a much, much simpler problem out of this in order to calculate the electric field due to a cylinder. Okay, and so now we can actually utilize this concept. Okay, so now we can use this concept to figure out the electric field.